Hello grade 12s, in today's video we're going to be looking at vertical projectile motion graphs. So this is going to be an overview of the 3 different types of graphs that you need to know for vertical projectile motion. I mentioned very important things relating to each graph, and we will dive deeper into each type of graph in its own video and we'll practice some questions, but you need to know the basics. You need to know how to contrast the 3 different types of graphs and how to recognize them, how to draw them, how to identify them, and important features and characteristics about each of them. So stay tuned for all the teacher tips and tricks I'll be giving throughout the video. Let's go. Vertical projectile motion graphs are a very important section of vertical projectile motion, and it can pop up in your exam in various forms. So for example, you can get questions where you actually have to do calculations like 3.2.1 through to 3.2.3. So you have to apply the equations of motion to answer different questions, work out velocity, acceleration, time, displacement, all of those things. And then you have to take those values that you've calculated and those that are given and use them to plot or draw a velocity versus time graph. So something like that. Here's another example of that where you have to do 2 objects on the same set of axes. So you can see that this one is worth 3 marks, this one's worth 5 marks, or an alternative way in which they can ask this is that they can provide you with a velocity versus time graph, and then they can ask you questions based off of that graph. So questions where you have to look at the graph, interpret the graph, extract values from the graph, or perform calculations using the graph. So obviously I've cut off the questions here, but you can just get an idea. So there are a numerous amounts of different graphs that you need to know. These are the graphs of motion that you need to know. Okay, so 3 different types of graphs. And our first type is position versus time. And you can see over here, I've written Y versus T because Y indicates position. Remember, we're dealing with vertical projectile motion, motion that is up or down or along the Y-axis, which is why I'm using Y to indicate position. Okay, so it's Y versus time. So position versus time. Then we've got velocity versus time. So how fast the thing is moving versus time. And then acceleration versus time. And you can see I've pasted 3 images here of what these graphs can look like. Obviously, they can look very different depending on the scenario. So for example, depending on if I've thrown a ball up or if I've dropped a ball or if it's a bouncing ball or whatever the case is. So in this video, I will be going over all the different types of graphs, what they look like, what they mean, things that we can calculate using the graph, how we can draw it, and important connections between the graphs. So this video might be a little bit on the longer side, but it's important that you stay throughout the entire video because I explain and I mention very, very important things that can cause you or can result in you getting 0 for the section or full marks for the section. So let's carry on. Right, my first graph is called a position versus time graph. So first things first, always, when you're dealing with a graph in physics or chemistry, I want you to take a look at the axes. So the y-axis, the x-axis, read what the axes labels are and the units. So if you take a look at this graph, you can see that we've got our y-axis being position, and this is position in the vertical direction, okay? Because we're doing vertical projectile motion. So it's how our y changes, how our position in the up-down direction changes, and then we've got time. So it's a position versus time graph. You'll see some weird green lines on the graph. I will explain what that means in a second, but this is a position versus time graph. And some important things about position versus time graphs. They tell me where the object is. It tells me about its position, so where it is, relative to some reference point. So the reference point can be the ground, it can be the top of a building, it can be whatever the question tells you that it is or whatever you select it to be. So let's pretend in this example that this is me throwing a cricket ball upwards, it's reaching a maximum height and it's traveling back downwards. So the reference point is like the 0 position. It could be my hands or the position where the ball was released from, or maybe it was shot upwards from the ground. In that case, my reference point is the ground. More often than not, your reference point is the ground. So we start at the ground, it goes up, the ball is literally traveling upwards, it's reaching a maximum height, and it's traveling back downwards. You can see how the curve looks. The curve of a position time graph, depending on the directions that you choose as positive or negative or what your reference point is, it mimics what the object is actually doing. So in this case, the object went from its starting position upwards, back down to where it started. Very straightforward, very simple. Now we get into some more interesting things. So it says here, the gradient. You know what gradient is? Gradient of a line. The gradient of the tangent of the graph equals the velocity of the object at that point. Now, we aren't really going to work with this in actual calculations, but it's good to know. And what all of those words mean is a tangent is a straight line that touches a curve or a curved surface at the point. Okay, so that is basically what a tangent is. So you can see that all these green lines over here are tangents. And if I take the velocity of each of these tangents, so if I take the gradient of each of these little tangents, so for example, if I have to work out the gradient of this little line over here, it will tell me the velocity of the object at that point. If I have to take the gradient over here, it'll tell me the velocity at that point. If I have to take the gradient over here, it'll tell me the velocity at that point, and so on. Now, take note how these tangents over here, this line, has an increasing slope. It has a positive gradient. Positive gradient, this will be a 0 gradient, and yet negative. Negative. And it makes sense because at this point over here, the object is traveling upwards. Okay, so it has a positive velocity. Here, the gradient is decreasing. Take a look at this green line versus this green line. You can see that initially the gradient is very steep and then it gets less steep, less steep, less steep until eventually here it's at 0. What's happening is it's telling me the velocity is decreasing until when we're at a maximum height, the velocity is 0. Then as we go down, these little tangents get more steep because the velocity is increasing. But each of these little lines have a negative gradient because the velocity is now in the negative direction. Okay, it gets a little complicated, it gets a little involved, but I hope that makes sense. I don't want you to stress out too much about this if this is a bit confusing, but what I do want you to know is that at the maximum height, so the object goes up, it reaches the maximum height and comes back down. At this maximum height, velocity is 0, okay? The gradient of the tangent, look at this line, that's a flat line. The gradient of that is 0. It's a flat line. Because that, the velocity is 0 at that point. Okay, maximum height velocity is 0. You should know that. Then I want you to know that over here, the velocity is positive. Over here, the velocity is negative. It's just the different directions in which the object is moving. As the object approaches maximum height, the velocity decreases. So over here, the velocity might be very, very high, like 10 meters per second. Over here, it might be 2 meters per second. Then at the top, it's 0. Then as it goes down, the velocity increases again. So it will go from 0, then 2 meters per second downwards, 3 meters per second downwards, back to 10 meters per second downwards. But it's negative because it's in the opposite direction. That is position versus time. And obviously, you get a whole lot of different variations on this depending on the situation. I will go through these different scenarios at a later stage in the video, but moving on to velocity versus time. Now, one thing that you should notice about a velocity versus time graph, and it will always be like this, is that a velocity versus time graph is a straight line. So I'm not sure if it's very clear on this graph behind me, but the velocity versus time graph is this straight line over here. It will always be a straight line. And the reason for that will become clear in a second, but just keep that in mind. Now, it might not always look like this. A velocity versus time graph, for example, could even just look as simple as something like that. But it's a straight line. It will never, ever curve. Now, a velocity versus time graph tells me how the speed, essentially, of the object is changing. So, if I have a situation where I drop an object off of the side of a building, so I'm just dropping it from here and it's going straight down, what can you tell me about the velocity of that object? The velocity doesn't stay the same. Think about it. You're dropping an object from rest. So initially it has a velocity of 0 from rest. It's not moving. It has no speed. It has no velocity. But as you drop it, what actually happens is that it gets faster and faster and faster as it moves down, which means the velocity increases as it moves downwards. So a graph like this could represent an object being dropped off the side of a building. Why? Because initially, at time 0, it has a velocity of 0. Then as time goes on, remember this x-axis is time, as time goes on, the velocity increases. So this would be a graph if I take downwards as positive. So initially the velocity is 0, then after 10 seconds, the velocity might be 20 meters per second. After 20 seconds, the velocity might be, 40 meters per second, but the velocity increases as the object falls down. And if down is positive, then the velocity just keeps getting bigger and bigger in the positive direction. I hope that makes sense. What are some things that you need to know about a velocity versus time graph? Now, the first thing is, and I've mentioned this already, the gradient is always going to be constant. That's why it's a straight line. It never curves. Same gradient for this entire line. And the reason why is because the gradient of a velocity time graph is acceleration. And acceleration is constant. What is acceleration? I hope you remember. It's 9.8 meters per second squared downwards. And it will always be 9.8 meters per second squared downwards if we're on Earth, which we are. So acceleration is always that value. Acceleration is always constant. Acceleration is always downwards. The gradient of a velocity versus time graph is acceleration. It is acceleration. And that's why it's a straight line. Okay, velocity time graph will always be a straight line, a linear graph with the equation y equals mx plus c. So basically the first 3 bullet points on this slide are saying the exact same thing. Now take a look at this gradient. Is that a positive gradient or is that a negative gradient? Well, the slope is going downwards, right? It's decreasing. Take a look at the slope. Take a look at the slope. It's going downwards. It's a negative gradient. It's a decreasing slope. The gradient is negative. And remember, the gradient is acceleration, which means that acceleration is negative. And acceleration is always down. So if acceleration is negative and acceleration is always down, that means that in this question, down is the negative direction, which means that up is the positive direction. That can be quite confusing, but I hope that that makes sense. Another important thing to note for velocity versus time graph is that when the graph is on the top of the axis, so in this, above the x-axis, remember, this is the x-axis. When the graph is above the x-axis, so for this little piece that I've circled, the object is moving in one direction. As soon as it crosses the x-axis, so for this portion, the object is moving in the opposite direction. And that is something very important that you can always be certain of, you can always be aware of. So if my velocity versus time graph looks like this one that I'm drawing in now, it means that the object is just moving in one direction. But as soon as there's a crossing of the x-axis, it means that it's moving in different directions. So what does this mean? It basically could mean that you have thrown an object, or you have dropped an object, or you've thrown an object upwards. Okay, it's going up in one direction and then it's dropping down in the next direction. So for this part of the graph, it's going up. For this part of the graph, it's going down. And that could correspond to this velocity versus time graph. Velocity versus time graphs are not easy. I will do a video where I go over this in more detail, so check out the link in the description box below for a more detailed video on velocity versus time graph. This is just an overview to help you understand the differences between the 3 graphs. Now, my last graph is the easiest graph of them all, and it is called the acceleration versus time graph. Now, as we mentioned, acceleration in vertical projectile motion is acceleration due to gravity, which is 9.8 meters per second squared downwards. So it's a constant value. So take a look at the acceleration versus time graph right here above my head. Do you see this blue line over here? That is constant. Acceleration is 9.8 meters per second. And that means it'll always be a horizontal, flat line. Just be careful. If we choose up as positive, stay with me. If we choose up as positive, which way does acceleration due to gravity go? So if up is positive, acceleration due to gravity is always down, so it's going to be negative 9.8. So if I have to draw an acceleration versus time graph, okay, the y-axis is acceleration in meters per second squared. The x-axis is time in seconds. This is 0. Yeah, the x-axis is 0. So if up is positive, acceleration is always down, which is negative. I need to draw my straight line underneath the x-axis. Please use a ruler, not like me. That would be negative 9.8. Because up is positive, so acceleration is down, which is negative. If you take down as positive, then acceleration due to gravity is also positive. So you won't draw your acceleration line over there. You'll draw it up here, positive 9.8. Just be aware of that. Now, what I'll be going through are various scenarios and how the graphs look for those different various scenarios. These are classic scenarios that can be asked in your tests and in your exams. So the first one is an object dropped from rest. Now, the first important thing to note is that we will often tell you to take the ground as the 0 position or the top of the building as the 0 position. That will change how your position versus time graph looks. So take a look at the 3 graphs. We've got position versus time, velocity versus time, acceleration versus time. Over here, you can see that my object starts, here's 0. My object starts at some height. Let's pretend it's 20 meters or whatever. And then you can see that the object was dropped and it falls downwards until it reaches the 0 position. So I hope that it's clear in this graph that the ground was chosen as my 0 reference or my 0 position, which means that when the object hits the ground, it's at 0. You could do a scenario where the building is chosen. So say it's dropped from a 20-meter building. We could tell you that the building is the 0 reference. Then your graph would look like this. Okay, here's 0. You're dropping it downwards. So this would be negative 20. You're dropping it downwards. But in this case, we are choosing the ground as our 0 reference. This is a common way to do it. And the position versus time graph is quite easy. It's quite straightforward. It's simple, I hope. It shows you literally where the object is, how the object is moving. Okay, where it is, what it's doing. The velocity versus time graph, remember, I mentioned it will always be a dead straight line like this, where it can be represented by the equation y equals mx plus c. It has a constant gradient, okay, because the gradient is acceleration. It's dropped from rest. Rest means that the initial velocity is 0. You can see here, initial velocity is 0. Then, as it's dropped, the velocity increases. And you might say, but ma'am, this is negatives. So the velocity is like negative 5, negative 10, negative 20, negative 25. So maybe when it hits the ground, it's negative 25. Why is it going negative? Well, what they've done in this question is they've obviously chosen up as positive, therefore down is negative. So when it falls down, the velocity gets more and more and more negative. Okay. If they've chosen up as positive and down as negative, it means that acceleration will be negative 9.8 because acceleration always goes downwards. And that makes sense because if you look at my acceleration versus time graph, here's my 0. This is negative, so that's negative 9.8. This all makes sense. Up is positive, down is negative. Right, this is basically very, very simple scenario. Just keep in mind that this is a straight line because the gradient of this is acceleration. So if you take the gradient of this line, if you had to work out the gradient, you should get the magnitude of 9.8. Our second scenario is an absolute classic. Okay, it's an object thrown upwards and it reaches a maximum height and then it returns back to its original starting position. This is what the graphs look like. We've got a position versus time graph, and I've shown you this one already. It literally mimics the motion of the ball. So it's thrown, let's say from the ground is my 0 reference, is thrown to a maximum height, and then it's thrown back down. Just take note that this would be y, not x. This graph, okay, is the velocity versus time graph. It is thrown with some initial velocity. As it travels upwards, the velocity decreases. Remember, at the maximum height, velocity is 0. Yeah, if you had to read that off, velocity is 0 at the maximum height. Then as it falls back down, velocity increases again, but in the negative direction. I'll go through this in a second.
But as you can see, once again, the velocity versus time graph is a straight line. Take note, is this an increasing or decreasing line? It's a decreasing line, which means it has a negative gradient, which means that acceleration is negative. And if you take a look at your acceleration versus time graph, that makes sense. Acceleration is negative 9.8. Here's another example of this graph. One thing that I do want you to take note of is the following, and I will go over this as well. Look at the area under this part of the curve. Look at the area under this part of the curve. Do you see that they are the same? And that is because the distance that it travels to go up is the same as the distance that it travels to go down. So what that means is that the area under the velocity time graph is displacement. So if I have to work out this area here, it'll tell me how far it traveled to reach its maximum height. If I have to work out this area over here, it'll tell me how far it traveled from its maximum height back down to the ground. All these graphs are connected. It's amazing. Right. The other thing that I want you to notice, and I've mentioned this before, is that when a velocity time graph is above the x-axis, so for this portion over here, the object is moving in one direction. So that corresponds to this, the object moving up, the object moving up. And I know it's confusing because this graph is going down, but remember, this is a velocity versus time graph. It doesn't tell me which way the object's moving. It's telling me what's happening to the velocity. So the object is moving up, but remember, it's slowing down when it moves up. That's why the velocity is decreasing, the object's slowing down. When it reaches its maximum height, velocity is 0. And then remember what I said, when the velocity versus time graph is below the x-axis, yeah, it's below the x-axis, it's moving in the opposite direction. So it's moving down. So these graphs, once again, are linked. And again, ask yourself, how does the gradient of this graph look? It's a negative gradient, which means that acceleration is negative 9.8, which it is. Look at the acceleration versus time graph. Now, a lot of the times that I get an aha moment, like from my students, when they're like, oh, yes, I get it. When I show them in more detail, the link between the position versus time graph and the velocity versus time graph using this particular scenario, or using the scenario where it passes the original point, which I will show you in a second. Just stay with me. The scenario that I'm talking about is this scenario. So we're throwing an object upwards, it comes back down, but then it passes that original starting point. So think of it as you're standing on a building, something like this. You're throwing an object upwards, and then it comes back down and it passes that original starting point. I will have a position versus time graph that looks like this. So you start at a certain height above the ground. In this case, the ground again is my zero reference. So let's pretend that I start with the building being 20 meters high. So this is 20 meters. You throw the object upwards, so it goes a little bit higher than its starting point. Then it comes back down and it goes past the original starting point to the ground. Take a look at the velocity versus time graph. I hope you can see that the area under the graph here is very different to the area under the graph over here. Now remember what I mentioned earlier. The area under the velocity time graph over here, or let's start by saying that, remember, when the velocity time graph is above the x-axis, the object is moving in one direction. When the velocity time graph is below the x-axis, the object is moving in the opposite direction. So where you see yellow, that's when the object is moving upwards. When you see blue, that's when the object is moving downwards. Now, which of these travels a further distance, the yellow or the blue? Well, obviously the blue, because for the yellow, you're just going from the top of the building up to the maximum height. For the blue, you're going from the maximum height all the way down to the ground. So the blue is a further distance, a further displacement, which is why the area under this part of the curve is a lot bigger than the area under this part of the curve. Okay, so again, these graphs are linked And they're linked in an amazing way. It makes it actually easy if you know what you're looking for. Remember, at its maximum height, velocity is 0. So now I'm going to show you how, just again, once more, because this will really, really help you. I'm going to link these two graphs and I'm going to color code it. Hopefully this is helpful. The object is starting at wherever we started. Let's say it's at the top of the building and it travels. We are projecting it upwards. Okay, so we're throwing an object upwards. Let's just draw a picture that corresponds with this scenario. Let's pretend it is, again, a scenario like this. However, in this case, the 0 reference is the top of the building. Okay, so we start at the top of the building. The object is moving upwards. Now think about this carefully. As you throw an object upwards, doesn't matter where you're starting from or where you're standing, if you throw an object upwards, it starts off going very fast. Then as the object travels upwards, remember, obviously pretend my hands aren't there, as the object travels upwards, it goes slower and slower and slower and slower and slower until it reaches its maximum height. So what's happening to the velocity? The velocity is decreasing. Look at the velocity versus time graph. The velocity is decreasing. So we start off with the velocity being at its maximum. This is just when it leaves your hand. So this corresponds to this. Okay, so let's say the velocity is 20 meters per second. Okay, you're throwing it upwards. That's why up is positive. Okay, cool. Then as it's traveling upwards, the speed is decreasing, which is why this line is going downwards. As it travels up, so basically what's happening now is as the object is going up, it's traveling higher, but the object is getting slower, which is why the velocity values are decreasing. So over here, it might be 15 meters per second, 10 meters per second, 5 meters per second, until eventually it gets to the top over here, where velocity is 0. So here, velocity is 0. So this part of the graph corresponds to that part of the graph. Again, the object is moving still upwards, which is why it's above the graph. So object moving up. Although it's moving slower, it's still moving up. Then it's at its maximum height. Then the object turns around. Here, it's going down. Okay, let's color code in a little bit better. Here, the object is going down. So it goes back down to its original starting position. So let's pretend that that is there. Now, remember, if it left my hand at 20 meters per second up, this velocity value over here will be 20 meters per second. Down, it'll be a negative 20. But then it carries on going. It goes further and further and further past its initial starting position, and it carries on like that. Okay, and it'll hit the ground with a much larger velocity. So let's say 30 meters per second, but negative because it's going down. Right, I hope that helps. I hope seeing it like that, actually, where you can connect the two, it actually makes a difference. Our last scenario that you need to be aware of that often pops up in exams is the bouncing ball scenario. So we can see here that the ball is bouncing, or let's say I'm dropping it from a certain height. So in this scenario, I'm dropping it from a height. It's bouncing downwards to the ground. It hits the ground. It bounces upwards again. You can see that my velocity versus time graph has two lines. The first line corresponds to when the ball is falling downwards and then hits the ground. The second line corresponds to when it bounces back upwards and reaches a maximum height. Here's another example. This curve corresponds to this curve over here. The bouncing ball, as you can see, in a real life scenario, you drop the ball from rest at a certain height. So say we're dropping it from a building again, 20 meters above the ground. It falls down to the ground. It's in contact with the ground for a short period of time. Then it bounces upwards again. Note how it doesn't reach the same maximum height. It reaches maybe 15 meters. The reason why is because when it's in contact with the ball, it loses some of its energy. It loses some of its kinetic energy. And it bounces upwards with a lower velocity and a lower height than the previous bounce. So that's how it looks. And this is the corresponding velocity versus time graph. So you drop it from rest, which is why the velocity is 0. Then as it falls down, velocity increases. It hits the ground. Then it bounces upwards. Now it's going up again. So in this stage of the motion, it's going down. Remember, when you're at the bottom of the velocity time graph, you're going one direction. When you're at the top of the velocity time graph, you're going in a different direction. So this is going up. This is going down. This is going up. This is going down. Just keep that in mind. And it does correspond with the curve. So here it's going down. Here we're going down. Here, the ball is going up again. And that corresponds with that. Then it reaches a maximum height, which is why velocity is 0 over there. And then it's coming back down, which is why the curve goes underneath. I really, really hope you understand how these graphs match up. It's super, super, super important. Then, the last thing that I'm going to go over for graphs. Okay, remember, I do go over all of these in more detail in their own individual videos, but I need you to understand how all three of these graphs are linked. So, position versus time graph, acceleration versus velocity versus time graph, acceleration versus time graph. First things first, if I take the gradient of the tangents of the position versus time graph, it gives me the velocity. If I take the gradient of the velocity versus time graph, it gives me acceleration. Okay, so remember, if I have a position versus time graph like this, and I take the gradient of the tangent. So remember, a tangent is a straight line that touches the curve at a point. If I take the gradient of that, it gives me the velocity. Okay? If I have a velocity versus time graph, so say a graph that looks like this, and I take the gradient of that graph, it gives me acceleration. So I hope you understand my little flow chart like that. If I go backwards, so let's work backwards quickly. If I look at the acceleration versus time graph, and let's say that this is recorded for 30 seconds. If I take the area under this graph, so with length times breadth, the area under the acceleration time graph gives me average velocity. So the area under the acceleration time graph gives me average velocity. But if I have a velocity versus time graph, and I've spoken about this already, if I take the area under the velocity versus time graph, this area over here, I get displacement or position. So it works backwards like that. Here's a summary of everything that I just mentioned over here. If you don't understand this little flow chart over here, you can just learn it like this. Okay, remember, when you're asked to sketch a graph or draw a graph, you need to always label your graph with the axes and the units. So for example, you can't just give me a graph like this. You need to label it. You need to tell me that this is velocity and it's measured in meters per second. And you need to tell me that this is time and it's measured in seconds. The question will always tell me exactly what I need to include on my graph. So you can see here, they tell you, I want this, I want this, I want this. If you don't include these things, you won't get your marks. And what you do is, in order to plot these things on the graph, you would have done calculations to get these things. So based on your previously calculated answers or information given in the question, you use those things to draw your graph. Now, I know that this was a long video. I hope that it was helpful. I do go through each graph individually, and I do some practice examples in the videos that are to come in the playlist. So I hope that you watch those. Please let me know what other videos you'd like to see, and I hope to see you in another video very soon. Bye, everyone.